Everyone, welcome to this video. In this video, I'll be presenting our demo for the project control of a nonlinear quantum magnetic levitation system in our course Digital Processing Design. This project was completed by Trevor Smith, Bilal Ayash, Kyle Snar, and Miriam Naim Ibrahim. To start off, we're going to take a look at our MATLAB code, and then we're going to take a look at a Simulink, and then we're going to look at the results. First of all, just before we start, we're going to take a look at our transfer function. This transfer function was modeled in our modeling report. If you want to refer to that for any questions or to understand how that came out, take a look at that. In our code over here, this transfer function is stored in sysdf, and that sysdf is basically switched into a state space. The reason we do that is because we wanted to create a stable system, and when we decided to run different controllers, we tried IMC. That didn't work really good, so the next move was to go with something that we're more familiar with or something we learned in class, and that's pole placement. When using pole placement, it's always easier to deal with it in state space rather than transfer functions. All right, we're going to take a look at this code right here. I'm going to run it, start off, and as you can see, the system that we have is unstable. Its transfer function is unstable. And as you can see over here, we have a positive pole that's really far to the right. So that's a problem, and then we have to fix that. First of all, we decided to design a controller, and we call that controller K. And I'm just gonna uncomment this to show you guys what's going on, and I'll explain what's happening. And all right, so using the MATLAB function place, the state feedback gain was calculated, which is K in this case. This provides the desired closed loop poles. We chose the poles to be a -20 plus 20i, -20 minus 20i, and -50. We decided to push it to the left side to make it those poles were we decided on those poles to achieve specific specifications that we chose with our group. Those specifications include an overshoot that is an undershoot that's less than 5 and an overshoot that's less than 5%, and a settling time of less than 0.5 seconds. We thought that this would be the best to model the system around, and that's what we did here. As you can see, we use the place function using the poles that I mentioned before. And using those functions, we can see that the system becomes stable now at 0 with this specifications right here, which meets our requirements, so it's a good go. Our next step was, as you can see, if you apply a unit step into the system, you're not gonna get the controller to follow that unit step. There's a little bit of problem there, and we decided to fix that using rscale. And the function rscale is really helpful. So as you can see over here, I'm going to uncomment this right here. So this n bar is a scale factor for the controller. The following MATLAB code was used to compute that n bar value. That n bar, due to the fact that that n bar is basically a ratio multiplied by the input, or multiplied by the input, to give you a more accurate or whatever you want. So if you input 0.001, you're gonna get 0.001, as you can see over here. So if our input is 0.001, we can see that stabilizes 0.001. all right. And the fact that the system has a rank of 1 and that is not equal to the n amount or state variables, that's not equal to our state variables, we have to fix that. And to fix that, we create an observer. The observer was designed to estimate those state variables while measuring the output y equals cx for the magnetic ball. As you can see over here, we decided to choose poles of -100, -101, -102. The reason we decided to do that is because we wanted the observer to be a lot faster than the system, and by pushing our poles to the negative side deeper, 5 times greater actually, which is 20 times 5, 20, referring to the polls that I commented on before, we see these amazing results. We see that the system does actually, or with the linear system, is stable and stabilizes at 0, as you can see over here. And I'm going to show you all the results of the final system on the Simulink file to explain what's going on rather than just showing you code. But just before we move into that, I wanted to show you that our observer is working really good. And by uncommenting this code and running this, you can see that, just give it a second, you can see that our observer is actually estimating our values really good. It started off a little bit sloppy, but then it catches on really accurately. As you can see over here, it matches it properly. And then the red lines are our heights, or h. The blue line is our h dot, and our I is our current. And you see that it matches really matches. The estimates are really good. All right, let's move on to the Simulink system, and then I'll explain basically those codes where, like, how did we implement that. From this code, the K value and the L value was used. The L value is exact same as the K value, but for the observer. The values are different though. The L value and the K value were used in our Simulink model because it's easier to just use place in MATLAB than in Simulink. As you can see over here, we have two systems. We have a nonlinear and a linear system. The only difference between those two systems is the plant itself. I'll get into that, but let's look at the linear system first. As you can see, this is our K controller basically, and this is everything below that is our observer that was used for making sure the system is stable. And this system, linear system right here, is just our A matrix, our C matrix, and our B matrix, A, B, and C. And it's just a state space representation of the system. We did it that way to simplify it for the demo, to make sure we could have used the state space block, but using this, it kind of clears everything out and makes sure that everyone is on the same page. And whenever we run this code, as you can see, that we have really great results with a little, like an undershoot that's really low, and stabilizes at -5 as inputted from our unit step. And that 0.005 is below the top. 0.005 below the top. As you can see, the system right here that we designed is working properly. So the only difference when we go to a nonlinear system is change the plant to the nonlinear plant without linearizing it basically. And as you can see over here, this is our nonlinear system. This follows the equation given on CourseLink, and it takes the voltage. The voltage is set to 15 volts, and you can refer to the modeling report to know exactly why we set that too. And the X in and X out just connects over here. And whenever I run that code, I don't get as nice results as I see from the linear, but the nonlinear is really acceptable results. As you can see over here, stabilizes in 1.2 seconds, around 1.2 seconds. And we see that it stabilizes at -5 times 10 to the power -3, which is what we really wanted. We see a little bit of undershoot and a little bit of overshoot, but that's okay. We assumed that this system would work on the actual system when applied. So yeah, this is our presentation for our project. If you have any questions, please feel free to email us. And thank you very much for listening. Have a great day. Bye.